So hi, we will get on with our discussion of shocks now, but before that I thought I should very briefly review our discussion of shock thickness. A, because it's an important topic, and B, because I'm afraid I misstated just one small point there. So very quickly, just to recap, we are now talking about thickness of shocks. Why are we even talking about this? Because ideally shocks have zero thickness. Right? But in real life, of course, in real life, not so in real life. In other words, in real life, shocks do have finite thicknesses, and so the question we are now asking is, what decides the thickness of the shock? And we found out during the discussion last time that it's the viscosity of the fluid which decides the thickness of the shock. Specifically, we also found out that we found out. Let me just say this. Fluid viscosity decides shock thickness. So these were the bottom lines of our discussion last time, and we also said that the thickness is something like a few mean free paths. Now immediately you should jump and say, well, the moment you say mean free path, it's no longer conforming to a fluid picture. It is true, you're right about that. But the thing is, you have a mathematically ideal discontinuity, and you're really talking about a thickness that is very, I'm expanding. This would be roughly the shock thickness, and this is a very expanded view. Really, this is very, very small. So when it comes to really small scales, okay, you are in any case, as you know, the fluid approximation holds for only large enough scales that are large enough so that they're not macroscopic, they're mesoscopic, they're between microscopic and macroscopic, right? But they're still large enough that you have many mean free paths inside them. And this kind of thickness is such that that assumption is on thin ice. In other words, the fact there might not be many mean free paths in between them. In fact, the shock thickness is only about one mean free path or maybe two mean free paths. Okay, and so here so the way we arrived at that was to show that at the shock, the viscous force, the viscous term, which is something like nu and the inertial term of both of these in the Navier-Stokes equation, right? Term which is rho u du dx, right? And when we write du dx, we are just considering one dimension for simplicity, balance each other. Why is this? Because in the bulk of the fluid is essentially inviscid. Okay, viscosity does not have any role to play at all. But when we start talking about large velocity jumps within very small lengths like this, okay, then what happens is du dx, okay, becomes large. In other words, there's a substantial change in the velocity over a very small length scale, okay, a very small length scale like this. So, du dx becomes appreciable and d square u dx square becomes even more so, even more appreciable. So, simply because this term is large, even though nu itself might be small, the combination is appreciable. And really, right at the shock, we are considering a situation where the viscous term pretty much balances the inertial term. And if you write this in order of magnitude terms, then in order of magnitude language, then this would be something like nu u over delta squared, where delta is the shock thickness, and this would be something like, I don't have space on this slide, but it's important to write it right on this slide. That's why I'm doing it. This would be something like rho u times u over delta, something like this. Okay, one u cancels each other. So, this nu u over delta squared should equal rho u squared over delta. Okay, and doing that yields the following important formula. The shock thickness is approximately equal to nu over u. It's very, very important, and this is the shock thickness. Up until this, we did not. Up until this, it's simple enough, right? So this essentially in support of this statement, the fluid viscosity decides the shock thickness. Of course, right? It's the viscosity here which decides the shock thickness. Also, of course, it's the fluid velocity, right? If the velocity is relatively small, then the shock thickness is relatively larger, and vice versa. So this is one thing. The other thing, of course, is to now ask, well, okay, this is a fluid property, but you said something about microscopics, you said something about mean free path. So what gives, right? So the thing is, the kinematic viscosity, which is something like centimeter squared per second, which is essentially some sort of a centimeter per second times centimeter, right, which is some kind of velocity times some kind of length. Yeah. So, what would the velocity be? The velocity would be the RMS velocity of the constituent molecules, and this length is not the shock thickness, it is the mean free path. Okay. This would be the mean free path. Okay. Now, what is VRMS? This is one of the mistakes I made last time. It's actually something like a square root of 3 kBt over m sub p. Kb is a Boltzmann constant, right? T is a temperature, and the square root extends all the way, of course, right? And m sub p is a proton mass. This is assuming that this is an electron proton gas. Okay. If it's not an electron proton gas, then this would be the effective mass of the molecules. Okay. If, for instance, oxygen is present, and that greatly overwhelms the proton. So this would essentially be the weight of an oxygen molecule. Okay. And this factor 3 is for monoatomic gas. So this is something like the order of unity, roughly. Now, what else is so let me write this down once more, and here you see the VRMS, the root mean squared, is something like and so this is one thing, and so let's try to compare this with something else that we know already, right? So what is the speed of sound, the isothermal speed of sound? Or for that matter, any, the speed of sound is also something like gamma kBt over m sub p. This looks very similar to this, okay, except this gamma can be 1 or 5/3, and here you have a 3. to the extent, in the manner in which we are working, we can confidently say that VRMS, okay, I made a mistake in the factor of m sub p when the last time we were doing this. That's the reason I wanted to emphasize this a little bit now. Okay, so now what happens is, so this is the main thing we basically said, VRMS is approximately the speed of sound. Okay, and now so this is one thing, and remember we also wrote down that the shock thickness, right, and nu is something like VRMS times lambda, in other words something like C sub s times lambda, because the C sub s is basically VRMS, right. So the nu is something like C sub s times lambda. Now what is the speed of the fluid right at the shock? Okay, it is something like C sub s, right. So the speed, the u at the shock, u is approximately C sub s. It might be twice C sub s, it might be 3 times C sub s, depending upon what the Mach number is, but to within a factor of unity, it's about C sub s. We are talking about moderately supersonic shocks. If that's the case, looking at this and this, right, we get this important thing, right. So shock thickness, the thickness is approximately the same as the mean free path. So the shock thickness, which we sketched here, this one, the thickness is one mean free path or 2 or 3 mean free paths. Why are we saying 2 or 3 mean free paths? Because we've played fast and loose with several of the factors of the order of unity that we've here, for instance, factors of the order of unity we've neglected. All right, so there might be a mistake of something like 1 or 2 or something like that, and so that is one place we made a significant, So therefore, this derivation that we've done, the shock thickness being equal to the mean free path, this is only approximately true, right. It might well be of the order of a few mean free paths. So I just wanted to emphasize this, primarily because this is not something you find discussed in several fluid dynamics texts or in discussions. Many of them just say that the shock is a infinitely thin discontinuity, and then they move ahead from that. Okay, so this is this was one important thing that I wanted to highlight. The other thing, as we go on, the other thing that I want to the next topic I want to cover is the issue of shock jump conditions. What do I mean by jump conditions? I mean, what are jumps in, say, fluid velocity, fluid pressure, fluid density, and things like that across a shock. Why is this important? This is the next natural thing to ask, right? We've been repeatedly saying that shocks are essentially discontinuities. Okay, if there are discontinuities, there are jumps, right? They are essentially jumps, right? So suppose this was a jump suppose this was a jump in density. Well, how much is this jump? That's the next question to ask, right? So how much is the jump in density? How large is this jump? So that is the thing that we will be trying to answer, and we will find that we will take recourse to the usual things, to the usual conservation laws, conservation of mass, momentum, and such things that we are already familiar with. This is not, yeah, okay. And the other thing I want to emphasize is that we will be deriving jump conditions, but what we will be deriving is for what's called a normal shock. We will derive these jumps for a normal shock. In other words, if this is a shock and this is the fluid velocity, they are normal to each other. Or the other way to put it is, the shock itself is like this and the shock normal is pointing in this direction, right? So, so the shock normal and the direction of the fluid flow are in the same direction. The shock is not oblique like this. Okay. This would be an example of a oblique shock, and this would be an example of a normal shock. Okay. For simplicity, we will simply be discussing this case, that of a normal shock. The jump conditions for an oblique shock are very similar, except they are a little more involved. I mean, it's just one more step. It does not it follows. If you understand how to derive the jump conditions for a normal shock, if you understand it thoroughly, it's not a big deal. Okay. The other thing to realize is that the jump conditions we will be deriving will only be the jump conditions on the normal component of the velocity, on this component of the velocity, and the normal component of the momentum. Mass doesn't matter, mass is a scalar, so only velocity. So the tangential components, this, those we assume to be continuous. However, there can be situations where there is not a shock at all. Okay, there is no shock. Okay, in other words, the normal components of the mass flux, the velocity flux, the momentum flux, these are all there is no jump in these quantities as you pass this new kind of discontinuity. However, there is a jump in the tangential component. Okay, so these are what are called tangential discontinuities, and these are not shocks. Okay, we will not be discussing this in any detail as we go ahead. That's not our main focus at this point. But I just wanted to sort of alert you to the fact that lest you go on thinking that the only kinds of discontinuities there are shocks. No, that's not true. Okay, there are these other kinds of discontinuities which are called tangential discontinuities, and one important tangential discontinuity is called a contact discontinuity. And what happens in a contact discontinuity is that only the density jumps across this discontinuity. The other quantities are all conserved. Conserved is not the right word. The other quantities are all continuous across a contact discontinuity. There's only a density jump. Okay, and so this contact discontinuity is also a bona fide discontinuity in the sense that there's a mathematical problem here. Okay, the density is discontinuous, it jumps. Okay, but the other quantities do not jump, and a contact discontinuity is an example of a tangential discontinuity, and it is not a shock. Okay, I just wanted to say this. We will not discuss this anymore. We will confine our attention to jumps, okay, for a normal shock, not even an oblique shock. We will confine our attention only to jumps for a normal shock. Okay, so as promised, we will now start talking about jump conditions, right? Jump conditions for a normal shock, right, a shock where this would be the shock, for instance, and the shock normal is pointing in this direction, and the fluid velocity is also pointing in the same direction as the shock normal. Okay, so this is what I mean by a normal shock. Okay, so before going into details, if this is the direction of the flow, right, upstream quantities, which would be this, this would be denoted by a subscript 1, and downstream quantities, which would be this, which would be denoted by subscript 2. In other words, assume that you are in a boat, yeah, going along with the stream like this, yeah, like this. So naturally, so you're down the stream here, quantity 2, and up the stream here, quantity 1. So suppose we are talking about something like u1 velocity. So the u sub 1 would be the velocity here, and u sub 2 would be the velocity here. Similarly, the density rho 1, rho 2, so on and so forth, p1, p2. This is what I mean by subscripts. Okay, so the way we go about deriving these jump conditions is we write down things like mass conservation, the fact that mass cannot be created or destroyed across a shock, and the way we write this down is, say, rho 1 u1 equals rho 2 u2. Now, what are we really conserving? Are we conserving mass itself? Are we conserving the mass flux? What are we conserving? In order to answer that, you simply look at the dimensions. The dimensions of rho are grams per centimeter cubed. You agree? And the dimensions of u are centimeter per second. So the quantity rho u has dimensions grams per right. So, and this is what the mass flux is. So really, a more accurate way of saying this is, this represents conservation of mass flux. That's what this represents. We say mass conservation, that's a bit of a loose term, but strictly speaking, what we're saying is the mass flux across a shock is conserved. In other words, rho 1 u1, which would, the mass flux in the upstream is equal to the mass flux in the downstream. So this is one important conservation quantity. The other thing is momentum. Again, momentum flux. Okay, we neglect viscosity. Why can we do this? This is very important. Why can we simply neglect viscosity? Why is it that we talked a lot, right? I mean, we are essentially now going to be using just Euler's equation. So again, we are of course talking about conservation of momentum flux. Just like we talked about conservation of mass flux, here we are now talking about conservation of momentum flux. And in doing so, we are going to be neglecting the terms that involve viscosity. Why is this? Because as we have remarked earlier, we are only, when we talk about the mass flux here, we are talking about the mass flux upstream or downstream, not near the shock. Okay, far upstream from the shock or far downstream from the shock. We are, similarly, when we write down the momentum flux in the upstream region, or we write down the momentum flux in the downstream region, both of these quantities refer to the fluid far away from the shock, either far upstream from the shock or far downstream from the shock. And we know that in these regions, the viscosity, the viscous terms are of no importance. Viscous terms assume importance only near the shock. Right? This is how we derive the shock thickness, remember. Viscous terms are important only very close to the shock. Away from the shock, it's essentially an inviscid fluid. So that's why we neglect viscosity. And so if we do this, what happens? The momentum flux, and this would be the upstream right, and this would be the downstream momentum flux, and we equate these to each other. And the upstream, again, like just to emphasize, the upstream momentum flux refers to the momentum flux far upstream from the shock. The downstream momentum flux refers to the momentum flux far downstream from the shock. That's why we don't need to, and because the fluid far upstream and far downstream are both essentially inviscid, that's why we don't need to add the viscous terms here. And if you look at the Euler equation, this is the pressure term, and this is what's called the Ram pressure term. Okay. This is associated with the kinetic energy of the fluid, kinetic energy per unit mass, of course, and this is just the pressure. And dimensionally, they are both on the same footing, otherwise we would not be able to add them together like we are doing now. So this is the first important equation. This is the second important equation. The third, of course, energy conservation. Okay, conservation of energy far upstream and far downstream. Again, really, this really means, so this would be the upstream energy flux, and this would be the downstream energy flux. Now we've introduced a new quantity W, and the W is the enthalpy. Okay. The difference being that the U squared, half U squared, this is essentially kinetic energy, right? I mean, kinetic energy per unit gram, right? So let me just write this down. Kinetic energy per unit gram of fluid, and the kinetic energy is essentially the energy due to the bulk flow of the fluid. However, this is the kinetic energy associated with the bulk flow of the fluid. It says nothing about whether the fluid is hot or cold or anything. This term contains, so it says it's only due to the bulk motion, whereas this term is the exact opposite. It has nothing to do with the bulk motion. You can be sitting in the fluid frame, okay, and this would be the energy per unit gram that you would see, and so this is representative of the internal energy. Internal energy. Of course, internal energy per gram. Internal energy per gram, right? Because there's also kinetic energy per gram, therefore whatever energy this is also has to be per gram. So this would be the kinetic energy per gram plus the internal energy per gram in the downstream region. This would be the kinetic energy per gram plus the internal energy per gram in the upstream region. So the internal energy has to do with heat, has to do with thermodynamics, and so that's called the enthalpy. And the enthalpy can be related to the usual, since this is a new quantity, the enthalpy can be related to the usual pressure and density like this. What this is really, this might be a slightly confusing way of writing it. It's essentially gamma over gamma minus 1 P over rho. This is enthalpy. Okay. So, so now we have three equations, and how many unknowns do we have? We have the density 1, velocity 2, and pressure 3, right? But so these are three variables, and you have two copies of these variables, right? One upstream copy, one downstream copy. So we have three equations and 6 unknowns. Obviously, we cannot solve for them, but we can solve for the ratios. With this, it's possible to solve for u1 over u2, rho 1 over rho 2, p1 over p2. And what are these? These are the jump conditions that we are after, right? So, so using these three equations, it's possible to solve for the jumps in velocity, density, pressure, and this is exactly what we are after.